So let's start.
Yes, please.
First, we'll have the quick revision session.
Yeah, very
Why
essential.
the last, like why the models came into picture, the more overview of this basically.
Yeah, Gopal sir is there. Gopal sir, I'm coming. Yeah.
So first of all,
Good evening, sir. Gopal sir. Good evening. One
Yes,
more
sir. Good
participant.
evening. Good evening.
One more participant is there. So we three are there. Yeah. Yeah.
So basically, we'll have the interactive session today. So what is RL? We all know. Starting from the scratch, what is RL? We all know that it's just trial and error, learning from the feedbacks, basically. Like the example of Pavlov's dog was given. And then coming to next thing, immediate versus delayed rewards. I have written actually the points which I'll cover. I'll go somewhat quick so that everything should be covered. So can you tell like what is the difference between immediate reward and delayed reward?
Okay, madam. So let me attempt. I started going through the notes once again. Let me understand. Okay. See, the reward is the one which we get by taking the immediate step. That means next step. Okay. Taking an action and going to the next state. Okay. Whereas the real reward actually comes somewhere down the path, end of the episode. We don't know. So since we don't know when do we get the final reward at the destination, so we try to add immediate rewards to get the value of the particular state. So immediate reward is the one which we tell us whether our move is right or wrong.
Okay.
So every state we take an action, a move, that the right is wrong, that immediate reward tells us. So,
or I can say a simple example. Let's take a cycling example, like, as a professor has taken that suppose you fall down, there was a stone. After some time, you tried to balance and fall down. That last step when you were balancing was not the issue. The issue was when the stone when you jumped on the stone, that was the issue. So it came, the delayed cost was there, or I can say it was not because of the last step the cost was given to you. It was because of that jumping on the stone, the delayed reward. That is basically the delayed reward, and immediate reward as soon as we got, that is the immediate reward. Now we also talked about the environment. The environment can be stochastic as well. Stochastic means noise, random as well. And then we came to what is, just someone brief out what is agent, what is policy, what is state, action. Just someone brief out quickly what are these.
environment is the real world. So environment has its own real world model, how the world works. Okay. So agent is the one within our, agent is basically reinforcement learning algorithm. So that agent is the one which actually tries to act in the real world. Okay. Taking the feedback and act in the real world, taking the feedback state and reward and acting the real world. So that is something which is a part of the reinforcement learning algorithm or the agent, which we are trying to learn. Okay. And policy is the one, we model the real world as a set of states and a set of actions for every state. Okay. So in order to achieve the goal from wherever you are in the current state, and we have to follow a particular policy. Policy means mapping from a state, given a state, what action do I have to take, which is the optimum towards reaching that particular goal. So every state, it is a mapping from a state to action. That action must lead to the reaching the optimum return.
Yes.
Return. Okay.
Yes.
So
basically, a state is there. We take a particular action. A reward is given to us, and accordingly the next state we go to. As you said, policy is basically mapping states to action, what action you should perform when you are in a particular state. That will tell like that policy will tell us. Is it okay? Now, sometimes we have also, okay, I'll come back to online learning afterwards. What is temporal difference? Yes. What is temporal difference? Can I say that the prediction I make at t+1 is probably more accurate than the prediction I make at t? If I want to make the prediction at t, I can go forward in time and see what is the prediction at t+1. Like,
yes, yes, ma'am. It is estimating from the estimation at t+1. Yeah.
Yes. If I say about the chess game, at the starting of the game, you make a prediction. At the mid of the game, you make the prediction. Obviously, the prediction that you make at the mid of the game is more probably correct than the prediction you make at the starting of the game. And at that point, you are more confident about the prediction than the beginning. That is what it means, TD learning. Basically, I'll go forward in time t+1 and then check, and then I will make, like, in order to improve the prediction I make at t, I can go forward in time and see what prediction I make at t+1. I know little bit better about the game after going forward. Use this, go back and modify the prediction point at t basically. Is it fine? Should I move forward?
Yes.
Okay. For everyone, it's fine? Okay. So, can I say in TD learning sometimes, okay, I'll come to that also. First of all, what is exploration versus exploitation dilemma? Yes. Yes, come on.
Since in any game, take the example of single state multi-arm bandit as an example, we don't know the expected return of a particular machine. Okay, so in order to discover it, we have to keep exploring it, to take multiple samples to find that expected return. But at the same time, we don't know which machine has the highest expected return. If we know it, we continue to pull that arm and get the maximum return. So the challenge is that we have n machines, or let us say a finite number of 10 machines. When we don't know which machine has the highest expected return, so we have to make a choice whether to explore continuously or explore once and when we find the maximum return and keep on exploiting the same thing. So it is like trade-off. When we excessively explore, we might waste a lot of our resources and get the net return. But at the same time, when we exploit greedily, that may not be optimal. That may be a suboptimal. We may be missing greater return by discovering other unexplored things. So it is like a trade. It's a dilemma.
Can I? You are absolutely correct. Can I say some example? Like, suppose I went to a hotel and I had the food there. A restaurant. I went to a restaurant. I had the food there, and suppose the cook was changed that time. But I thought, okay, the food of that restaurant one is not good because the cook was absent that time. The main cook was absent, and I didn't explore much. And I went to the other restaurant and said that it's the best one. Because of the less exploring of that restaurant one, that is the reason I didn't find that restaurant one better than the restaurant two. Maybe because of the stochastic nature or something that happened at that day, that restaurant one was not good because of the cook was absent or any other thing. So basically, or the other example which professor gave, if drug 1 and drug 2 are there, and microorganisms, we want to see that whether they survive or not. By seeing for the one time, we can't say, okay, we tested the drug 1 and microorganisms survived. We can't say that drug 1 is the best one. We have to explore the other one also, and then we have to come into conclusion. There is a time we have to decide whether we have to stop exploring and start exploiting. And sometimes it is dynamic also. We'll come to that also by in the map technique. Before now going to banded optimalities, before going to banded optimalities, I forget, okay, why is TD learning introduced? Basically, why TD learning came to picture? Can I say waiting till end and keeping history of all the states and action is tedious? It is difficult to keep the state and action, all the history of all the state and action. That is why TD learning came into picture. Though we'll see in the detail in after coming.
Yes, particularly when we have a large state space and action space, one episode of trial from any state is very long, and it's not practical to store all that. And
as we saw tic-tac-toe example, it was like only we have to store only 9 states there. But if we say about the chess and all, storing all the history, in tic-tac-toe example, we saw either we can store the, like if we are not using TD learning, what we can do is we can store all the history, and we can say, okay, we win the game, now we'll update our reward. Or we can play various games and say, okay, this game we won, and that is why we won, because we took that and that action. This is how it is done. But it is like we are storing so much of history. Tic-tac-toe is just 9 states, it's fine. But if we talk about the other games like chess, storing the history, it becomes difficult. That is why we switch to TD learning in some places. Coming to banded optimalities, we discuss some properties: asymptotic correctness, regret optimality, and pack optimality. So can you give me the brief about all of these? Someone among you?
I haven't read in deep, but I know that they're all concerned with the sample complexity.
Okay, anyone else? Yes, come on.
Yeah, sample complexity means the less number of samples to discover optimum is better. So that all these 3 techniques give an idea or a bound on the optimality we can achieve, something like that vaguely. But okay. So maybe someone else can.
Can someone explain in detail about this?
Yeah, I think for regret optimality, it's basically like you're trying to minimize the regret. So if you pick the best action from the start, and now if you're learning and then you're learning and then you're converging to the optimal, so the difference in the return is nothing but the regret, and so we are trying to minimize that regret.
Okay, and what about asymptotic correctness?
Yeah, that one I don't remember exactly. Pack I remember, and regret I remember.
Okay.
Madam, I try to explain my understanding. Asymptotic means, you keep on exploring randomly, okay? All the machines, and at some point, at infinitely, when you keep exploring, you ultimately will discover, will converge to that, but at a great cost of exploring too many samples.
Correct.
Okay.
What about pack optimality?
Pack is this, yeah, it's probably approximately correct. So we have we have we will converge to a epsilon. I don't know I don't remember the terminology, but we'll be close to the optimal policy with an probability with high probability, and that is also within the bounds.
Yes,
so it's
yes.
probably approximately correct solution.
Yes, correct. Basically, if I talk about asymptotic correctness, it means if I put no bounds on you, it will give the guarantee that you will select the arm which will give me the highest payoff. Or I can say in the MAB approach, if I apply MAB approach infinite times, any of the MAB approach infinite times, algorithm will always converge to optimal or near optimal. Or if I increase the, like if I in the long duration, I'll say that algorithm will end up exploiting the best arm to maximize the reward basically. That is basically asymptotic correctness. I will choose the best arm in the long run. If I'll go till infinity or if I'll in long duration, I'll always choose the best arm, which is giving me the best maximize reward basically. Coming about the reward optimality, regret optimality. So basically, can you tell me the difference between these two? Here I am exploring less. What do you mean by exploring less, and what is the consequence of this?
Yeah, we are close to the optimal, but we have not yet reached optimal. So our uh, our regret will be infinity because we always
Because the
are less
exploration
than the
was less. Mhm.
yeah,
And
less than the
here,
possible maximum possible reward.
So basically here I was exploring more. I don't know in the starting which is the best arm, so I explore more, and then after some time I'll do that. Here initially I tried to reduce the regret only. Just I started exploiting by considering, okay, this is the best arm. It may be the case we miss out a certain key or certain thing by exploration, that because of the exploration and trying to have this because we want to have this little regret. And sometimes it's fine for us also, because if sometimes we are okay with the suboptimal arm but we want the time, that regret timeless, then this second thing is okay. But if we want more optimal arm, then left thing is okay with us. So we should have that trade-off, like how much regret we should have and how much like basically explore and exploit. If I talk about probably approximately correct pack optimality, that is basically, as you told, that is probably approximately correct, and with some of the error, like some epsilon error, that is basically pack epsilon optimal, we say that term. If true arm and the we have the sample one, they have the difference of the epsilon, and with some confidence we are saying that the difference between the optimal arm and the arm which we have chosen, that is the difference is epsilon with delta confidence, that is basically epsilon pack optimal. So basically we say it probably approximately correct what we are choosing the arm basically. Or arm is very close in payoff to the best optimal arm, epsilon close to that with 1 minus delta confidence, we are saying that. Now coming to map techniques. Is the speed correct, or should I be more slow, or is it fine? Is it going smooth, the revision process?
It's fine, madam. Considering the amount of syllabus, it's fine.
Okay. Now coming to this map techniques, I can say we have greedy, as everyone said, that just some table type, okay, epsilon greedy, soft max, and Thompson sampling, and UCB as well. I'll consider UCB afterwards. Okay, consider it together. So what do you think, what is the limitation in each of them that we came? This was the doubt, that how we came forward, that what was the limitation is in greedy that we came to epsilon greedy, what is the limitation in epsilon greedy that we came to soft max, or what is the limitation in soft max that we opted for Thompson sampling? Okay, can someone explain me first of all what is greedy? First of all, let's focus into greedy and epsilon greedy. What is the limitation between greedy that we, what is greedy approach, what is the limitation for the greedy that we came to epsilon greedy? First question. Yes.
See, I only know the method means, madam. Okay, assume that we have 10 machines, bandit
Okay.
machines, and so you sample each each
Okay.
machine once
Okay.
and find out the maximum return in one sample each, and whichever
Yes.
is the machine, you keep on pulling it. That is
Okay,
greedy.
greedy. Yes. What is the limitation? What do you think? You said the method correctly, that I'll go to each arm, I'll pick up the each arm, I'll see the reward, and whichever is having the maximum one, I'll keep on pulling it. Absolutely correct.
Yeah.
Now, what is the limitation of greedy that we came?
Yeah, the reason is since the machines are stochastic, so we don't know whatever we picked up, maybe giving a high reward just in that sample. Maybe the other machine has a higher expectation, okay, which we did not, which we did not pursue with more samples. So
Yes,
we may be missing the good one, okay, which may not have surfaced in our first trial. Yeah. That's it.
Yes, absolutely correct. Suppose first time A gave me the best one, and I thought, okay, A is the best one only. I'll keep on pulling A. But maybe after some time, the C is giving me the best reward. After some time afterwards, it changes, and for the probability, the C gave me the better one, and C is the best arm. But I am pulling just the A arm because at the first go only, A gave me the best reward. That is what, because of the stochasticity, we can say. And now coming to epsilon greedy. What is epsilon? So there is a limitation that we are not exploring enough, and we are not exploring actually in the greedy. That is why we shifted to epsilon greedy. Fine. Now, what is epsilon greedy? Now we know that why we came to epsilon greedy. But what is epsilon greedy approach? Now the limitation was exploration is not done. How we are doing exploration in epsilon greedy?
With the probability epsilon, we explore, and with 1 minus epsilon probability, we exploit a greedy.
Yes. So with now we thought, okay, the exploration is not there in the greedy. Let's have some exploration. So with epsilon, we'll basically with 1 minus epsilon, with epsilon we'll explore, and with 1 minus epsilon we'll exploit. Okay, that's correct. Now, what was the limitation in epsilon greedy that we shifted to softmax?
See, even with this e-greedy, because we continuously we may end up greedy, and we may not exploit, we may not discover still unexplored. Maybe there may be still unexplored things might have been left out in even epsilon greedy. So what happens is that in softmax kind of algorithms so we reduce our basically our exploration. Okay, the machines which we explored already, which were not explored, are given higher probability to explore. Maybe something like that. I don't know. Maybe
someone else would give the answer. What is the limitation of this epsilon greedy that we shifted to softmax?
As time progresses, we should somehow reduce exploration, which is not happening there. So we can use softmax to do that.
Okay. Can I say in other words, okay, suppose I have two actions, action 1 and action 2, and the difference between the rewards is like 0.001, whereas the others are also there, action 3. They are bad arms, but they are action 2 is also arm 2, sorry. Arm 2 is also treated as arm 3, arm 4, but still it is very nearby to arm 1. Still it is treated in that category. Or the other thing I can say is the one more limitation is there, that lesser one. Okay. One more limitation. Okay, as you pointed out, that suppose arm 1 and arm 2 is there, and arm 2 suppose is basically, I know that arm 1 is now the best arm. Still, I am always giving 10% or 0.1 probability to arm 2, arm 3, arm 4. I definitely know that arm 4 is not the best one. Still, I am exploring it 10% of time. Why? There is no need to explore now because I know this is not the good one. or I have to reduce their exploration, but we are keeping this fixed probability of the exploration there. Am I correct by saying these things? Now we come to softmax. Now in softmax, what we are doing is, we are basically, there is a temperature parameter. We are saying how much we should explore, how much it should be more exploratory or more greedy. We have that in our hand, that we should make it more exploratory or we should make it more greedy. So that is the main point which softmax is having. Beta is the parameter which will help us to control. Just write it. Arm A is the arm which we are picking, beta is the parameter which we are exploring, and the other arms are the denominator. So this is basically, that is why softmax came into picture, to have the that thing in our hand, how much we should act more greedily or how much we should explore. Because sometimes exploration is also not needed. We have to stop it or we have to lower it down because we know that now this is the best arm. Now coming to the other algorithm, Thompson sampling. I'll come. Okay, what do you think? What is Thompson sampling? What is the difference between softmax? Why we are shifting to Thompson sampling? Or softmax is as good? So what are your views about this? Yes. What is this theorem?
Bayes theorem.
Bayes theorem. So what is the prior belief here? What is the posterior belief here?
Posterior is A given B, and prior is probability of A.
So basically in Thompson sampling, we update a posterior according to prior. Or in the other words, I can say that what we are doing is, I have arm 1, okay, I'll take that. So basically I'll do this beta distribution. I have the arms, I'll do the beta distribution, sample the theta out of it, and then check what is the argmax basically, what is the, which one is them, and then update the alpha and beta accordingly, whatever reward is given to me. Suppose I have the two arms, arm 1, arm 2, both beta is basically 1, 1, 1, and I sample it. And suppose arm 1 give me the better reward, so I'll update the alpha, basically alpha plus 1, and beta will be as such, which means it will be beta 2, 1, and it will sample again. So basically it takes care of the exploration and exploitation accordingly. We don't have any, like, if I talk about the softmax, I have to till that I have to, that is the knob which is in my hand, that I have to make it more exploratory or more greedy. But in Thompson sampling, it do it themselves. It is dynamic, like it will take care of the exploration as well as the exploitation, because that randomness is already induced in that Thompson sampling. So that is what is the advantage of the Thompson sampling. If I come to the UCB, UCB is also good, as good as Thompson sampling. Actually, when UCB came to picture, that time Thompson sampling is older than UCB. But I can say when UCB came into picture, that time Thompson sampling was not that popular. But then after that, after some time, Thompson sampling also got that popular. So both are as good, we can say. But here we are dealing with more of the probability distribution and all in Thompson sampling. And coming about UCB, can someone tell me what is UCB? Yes. Yes, come on.
There is some standard deviation term added to the average return.
Yes. Can I say a second? That
And then based upon that addition and which maximizes, it will select that term.
So basically, we first of all play the arm at least once. That is for
Yeah.
everyone.
Mm.
Then
This is the standard deviation term. Yeah.
so number of times played each arm divided by number of times played that arm J basically, or I can say the confidence interval is there. So can I say in here also this CI, this interval is there. So can I say here also the randomness is taken, the exploration part is taken care itself
Yes.
only. So
Yes.
basically UCB and TS, that is why I was saying they are both as good as that, but their methodology is different. They both take care of exploration part themselves. We don't have to take care of that one. Basically, UCB is managing the uncertainty by adding the confidence bound basically, and TS is managing the uncertainty by maintaining the probability distribution, I can say. Okay, one more question I want to ask. If I talk about the exploration, is exploration is deterministic in UCB? In which exploration is deterministic or probabilistic? In TS and UCB, what are your views? Any rough idea?
What is meant by this?
Okay,
Yeah.
because of something I'll explore, or because of some factor. If some factor is there, then only I'll explore, or it's like randomly I'll explore. Okay, I'll give you. If suppose if I talk about UCB, as we have seen some diagram, suppose this is Q1, this is Q2, and okay, I'll take it, and this is Q3, and this is Q4. So I'll explore whosoever is not explored, because after seeing the confidence bound, can I say all the algorithm will pick the action with the highest UCB upper confidence bound?
Yes.
That is deterministic, I can say. On the other hand, Thompson sampling, the actions are based on the posterior distribution, more stochastic, I can say. Exploration is stochastic, if in that sense we can see.
Yeah. Okay.
This is the different view I am giving just to the same thing.
Okay.
Now, coming to these were the map techniques. Any doubts in the map techniques? Are they clear? Okay. Then we came to concentration inequalities. I think so. I have cleared this, how the other map technique came into picture. Now coming to the concentration inequalities. Basically, concentration inequality means that I have some number of samples through which I'm like estimating the expectation, and I am having the true expectation as well. So how the number of samples, or how quickly or how slowly my estimation is approaching to the true expectation. True basically, or I can say that if I give the example, it's used many times, that is why I'm revising. Simply I'll write the formula. Chernoff Hofting bound we have done. So basically, how far is my estimated mean from the true mean? This is estimated. This my concentration inequality or Chernoff bound is giving me. How my estimated mean is far from the true mean, basically. How much is it far? That is basically it is giving me. This is basically used in UCB theorem proof, which I'm not going to do. Just I was revising this formula only. Now, the next topic comes about the background also bounds. I will not give the proofs of that. Okay. policy gradient and all, we'll study in the full RL thing when I come to that. Now coming to contextual bandit. We studied about map techniques. Now what is contextual bandit?
Madam, what is map actually? I forgot. Is it maximum a priori?
Map is these techniques. Basically, they come under map, multi-arm bandit. I want to present this one arm basically, which is the optimal. These techniques, they are map techniques here. Okay. Now coming to contextual bandits. Can someone tell me quickly what is contextual bandit by giving an example? Yes, come on.
This clicking advertisement example, like that.
Yes.
There are clicking advertisement example.
Yes. Yeah. What is contextual bandit? Is
So,
it same as map or some difference? Or
there are states. There are states over here.
Okay, there are states. How is it different from full RL? I have map, I have contextual bandit, I have full RL problem. Okay,
here,
it is
expectation change, madam. So it's actually stationary. Expectation changes with the sampling.
So in full RL also it change. Can I say that it's not like you give me an action and that will depend, like suppose I am in the state and the action is performed, then it will be dependent on S1 basically. Some action is performed and now A1 is in full RL, A1 is dependent on A2 basically. It's not like that. It's not sequential basically. No sequential dependence is there. I'll come 1 minute in detail what I mean by no sequential dependence. I will give you a state. Action is given to me by policy. Now I went to S2. I am in some other state. I perform an action. I went to S2. It's not like you give, it is independent of what action you selected. I will give another state basically. It's not like a sequential process. If I'm in S, I have to go in S1, then other action. This A2 will depend on A1 in full RL. It will depend on what previous action you perform. I can say it is like multiple map basically problem. I am in the state, what action you have to perform in that particular state. Then I am in totally different state, then what action is performed. That previous action is independent of this current action basically. That is basically contextual bandit. And yes, there are states unlike map technique. Now, as he gave the example of add, basically, yes, this is the example. And one more thing, like in the example, we can add, suppose I want to show add to a particular group of people. So I will look at the browsing history accounts, and I'll show different ads to the different set of peoples, basically. I'll not show the same thing to everyone. I'll not perform the same action for the every state, I need to say. And for the state, for the one person, the action can be different, and for the other person, it can be different here. Now, coming to full RL problem. As we have discussed about agent, environment, actions, states, as well as the rewards. We know about the whole process. There is environment, agent interact with the environment. In response, agent takes action, which is then applied to the environment. Environment takes, gives the reward and goes to the next state. And accordingly, the next action is taken. Now, coming to So now get discounted. Okay.
Madam, just one clarification. In most of the grid world problems, I always get confused about representing the immediate rewards. So, for example, in each world cell, if you indicate a number, let us say 1 or 0, is that mean that the immediate reward upon entering the state, or the reward you get after leaving the state to the next? I see.
Actually,
Yeah, that RT and RT plus 1, I get confused.
actually, some say that, okay, I am in the state, I take that action, and then the reward is given to me, I take it to the next state.
Yeah.
Some say that it is RT plus 1, basically, we are entering the next, basically. Or we can say that RT also, we are in the same state. I don't think so, it matters a lot. I'm a state, I'm in the action, and then the reward is given to me, and then I'll go to the next state. Just remember this.
Okay. Reward is given to me, then go to next state, or after the next state?
No. After going to next state, I'll get the reward, and then I'll go to the next state.
Oh, okay. So in the problems, no, the immediate reward is represented as part of the current state or the next state. Sometimes some problems we take immediate reward actually from the state, not from the current state. Maybe I don't know, representing the numbers. For example, if you want to represent all the immediate rewards in a grid world, what does that indicate? Suppose if you draw a grid world and put numbers there, 1 0 or 1 minus 1 minus 1 0 or something.
Actually, if I am in the state, I take the action. Sometimes I'll represent it as RT or RT plus 1. That is what is your question?
Yes.
Just remember this, that if you will take a state, if you are in the state, you take an action, then the reward is given to you. Sometimes we denote it by the time plus 1, the next t, or we in some places it is denoted RT as well. It doesn't matter. Don't go in that much like via RT. Just remember, after state action, and the reward will be given to you. Then only the next state will be performed.
Okay, madam. Go ahead.
So why the discounted rewards, average reward return and all, they came into picture in this RN techniques? What do you think? What is the advantage of each of them? What is the disadvantage? Why they came? Yes. Come on. You all know. Yes.
Yeah, so that is how the agent will keep on experimenting and will get the awards at the current time, next time, till it reaches to final goal, till episode ends, and then.
Can I say it deals with when we have infinite that thing? That is why we do this discounted and average reward RL.
Sort of, yeah. Yes.
When we have a long-term reward, that long-term basically, so we have to quantify with something. That is why we are taking discounted, and discounted rewards also have that far-sighted and near-sighted.
Yeah, far-sighted and near-sighted. Yeah, yes. Gamma is one. It is far-sighted. Gamma. Yeah.
Okay. So can I say if it is close to 0, it's near-sighted?
Yeah.
And what do you mean by far-sighted and near-sighted? Can you explain in detail?
So if gamma is 1, no? Gamma is close to 1, right? Even future rewards after, let's say, many time instants after will also matter to this.
Can I say if it is 1, then it is equal to that MDP, it's equal to taking no discounted, now no discount rewards, it's same as taking no discounts.
Yes. So far, rewards in far future also matters at this moment. Yeah.
And nearsighted means the immediate one. Can I say that?
Closer ones. Yeah.
Closer ones, we can say.
And and also the reason is we select gamma is less than 1 to ensure that it doesn't become infinite, the return. It converts to finite value.
Yes. So sometimes the near one are more valuable to us to the last one. So that is why this discounted reward theory came into picture. Now, what is average reward return? Or can you tell me what is the limitation of discounted reward, or what is the limitation? Both have some pros and cons. How each of one is better than the other? In which situation? Which one will apply? Yes, come on. I'm just a rough idea. What do you think? What do you guys think?
I mean, the thing is, this average rewards, I think there are, mathematical proofs are available, I think. But practically, it is not possible to have average rewards.
One
So
more thing. Okay, and one thing that we discuss now, it's fine. Yes, you are correct that mathematical proofs are there. We studied that practically it's difficult. But one more thing, sometimes we want to give more value to the near one and lesser value to the far-sighted one. In that case, can I say discounted rewards are better?
certainly, yes.
And when does discounted rewards create a problem? Okay, we discussed, okay, average reward creates a problem sometimes in this case or sometimes in practicality thing. When does discounted rewards create a
So
problem?
selecting gamma value, it's a domain, experts, we require, expertise in the domain to select gamma value.
Yes.
Selection, yeah.
Basically, some people take it as hyperparameter, which is not a correct. We are changing the problem, tuning a problem in our own way, which is not the correct approach, I can say.
Yeah, yes.
So that is why
Gamma will change the solution.
Gamma will change the solution. That is what comes into picture. Now coming to value function. Value function and Q function. So basically value function is if I have state, then what is the expected return, and Q function I can say is, we have studied a lot of time that when we are given with the state as well as the action, then what is the expected return?
Madam, some clarification about the notation. In some places, I see return instead of GT, capital RT. Is the same or?
Okay. What other thing, is it the same or not?
Capital RT is small r. Small r is small r, capital R. I always get confused, even though I looked at the terminology in the book.
Sometimes they are taking the reward. This is the return, basically. It depends on the context, like what they are taking.
Capital RT versus capital GT.
Is it the reward and return, I think?
Is it Q by S comma A or only S?
Q pi is S comma A only, na?
S comma here on the left hand side.
Okay. Yes, you're correct.
Yeah. Small q and capital Q. Okay, what's the major difference?
I'll come to that. Don't worry. I'll come to that. True value expected, I'll come to that. Till now, what we have done, value function and Q function. If the state is given to me, expected return. If the state and action are given to me, and what is the expected return? Here, the first action, we don't know. In the Q function, is it the optimal one? We don't know. It's not the optimal one. We don't get it. But in value function, we try to make that first action as well as first action also the optimal one. That is what is the main difference between them. What is a Markov assumption? Basically, can I say that first Markov assumption is that we are not depending on the whole history. We are depending on the current state and the action. That is the first state Markov assumption.
Yes.
Okay. Now, We studied about map, we studied about V and Q, what is that? We studied what is Markov assumption. Now jumping to MDP. Markov decision process. We have state, action, reward, everything. Transition probabilities are given to us. This is basically model based, where whole model is given to us, where transition probability is provided to us, where the reward is provided to us. Oh, sorry, transition probability is provided to us. This is basically called as model based, basically MDP. So we had done the example. I think I'll not repeat that example, that the robot is basically searching for the cans and all. Then there is a reward. We did the whole, and we also did, I think, machine replacement, some machine example also of MDP. Okay, let's proceed now to the value, Bellman equation. It's not working. Okay. Suddenly my pencil stopped working.
This is stochasticity.
Okay, now coming to Bellman equation.
Madam, here,
Yes.
madam, here one question. In the value function of V of S and Q of S comma A, are they always with reference to a policy, right? We always put policy as a superfix, correct?
Yes.
Always with reference to a policy, correct?
Can I say V star of A? V star of S?
No,
What is
no. V star means optimal policy. But normally, but if you don't, but no. See, in some books, they don't put any superfix of pi. But without pi, we cannot calculate value of state, value functions, right? See, always value functions, whether V of S or Q of S comma A, can only be computed with reference to a policy, whatever may be. That is something random policy or whatever it is.
Yes,
So,
yes.
can I say that even if we omit that symbol, it is assumed that V superfix pi is always there.
Yes, yes, yes.
Okay.
Now coming to this Bellman equation. Last time you were only saying that this is the main thing in the course. We have reached there. Okay, just go line by line, by word, like what is this V pi of S? What is this? And explain. First of all, what is go element by element? What is this? What is this? What is this? Yes.
Yeah, the first one is the policy.
What is this SA? What is this whole?
That is that is a policy, stochastic policy.
Can I say
state,
if I am
given a
yes.
state, yes, what is the probability of action?
Okay, so given a state is, what is the probability of the action I'll take? Okay, now I have the action as well as the state. Then?
Yes, then we compute probability of next state. That is
Okay.
MDP. That is MDP.
Yes, now?
Here, this is, here the one thing, madam, here only confusion. Is the reward R is stochastic or deterministic?
It can be both.
Okay, then in that case, we have to put P of R.
If it is deterministic, can we take just R there? Do we need to take expected value of R?
We are taking expected value of R just so that if it's deterministic or stochastic, we are keeping it like that only. If it's deterministic, it's R only, expected of expected. So that is why we are not differentiating between deterministic, stochastic. If I'll take deterministic, it's R only.
But
Okay.
in most of our analysis in the entire books and all, we always take deterministic, consider R as a deterministic, right? Nowhere we consider the problems involving stochastic rewards, immediate rewards.
Is it
I-
like that?
Huh?
I don't.
This
I
is
think-
immediate reward, right? R is
Expected immediate expected reward. This is
immediate
immediate
expected reward.
Yes,
Yeah.
yes.
Immediate no.
Immediate expected reward, correct. Now this is the future one.
Okay.
Probability that this will be the expected return, or that is the future one. So basically, start in S, select the action according to the probability pi, then determine what is the, now I have the state, I have the action, then what is the S bar, determine what is the S bar. Now what is the expected return reward you get after going to the S bar, and then basically the future, like what is the probability that it will be what will be the expected return, what will be the expected value function, the future one.
1 minute, madam. Here only to untangle my confusion regarding the terminology. One is reward, which I understand, which is immediate reward. Then next concept is expected reward. Okay, that when we say expected reward, we are assuming the reward is stochastic, correct?
Yes,
Okay.
yes.
Then the next term is return. Return is a cumulative summation of the rewards, correct?
Yes, yes.
Yes. That is next. The fourth term is V of S. So V of S is nothing but expected return. Maximum. Okay, sorry. It is just an expected return, right? V of S.
What other thing? What is V of S?
Is nothing but expected return starting from that state towards the goal.
Can I say?
It's a backup. I mean, backup from next state. Yeah, to compute V pi of S, right? You're saying.
Yeah, I'm generally saying V pi of S. Okay.
Yeah, V pi of S is a value function, and V pi of S prime is a backup, right, from next state. Yeah.
Yeah. Okay.
Future state, basically expected return of the future.
Future state.
Cumulative future. Yes.
Yes. Yes.
Yeah, V pi of S is the current.
Yeah.
It's the current state from current
Value
state.
function. Value
Yeah.
function.
Yes.
Yeah. No. Value function is okay. I'm trying to define what is the value. The value is nothing but return only, right?
Yes. It's return only.
Yes.
Okay.
Yes.
Okay. Got it. Thank you.
It's expected return. That first
Yes,
equation was given. No. Expected
Yes.
with respect to pi.
Yes. Correct. Got it.
Basically expected return, or I can say cumulative future reward. I can say the same thing only. Okay. Now coming to Q pi of S. So can someone explain me what is this? Come on. Yes.
Yeah. So this is the action value function when we take action A in state S.
Yes. Can I say it's same as that? Just we are taking action only. That is the difference.
Yes.
The probability of taking S and A, then if S and A are given, then what is the S dash, and then what is the expected reward? The same as earlier, and this term is like S, and then what is the, if I am in the S bar, then this is.
Madam, the bottom one expression that gamma sigma a dash pi, the whole thing becomes gamma into V pi of S dash, correct?
Yes.
Mm,
Yes, it is V pi of S dash. Yeah.
yeah,
V pi of-
V of S
Yes.
dash. Yeah.
So that is a beautiful equation which connects V pi and Q pi.
I'll write it. V pi of S is equal to, I think it's summation of A only. Pi of A. I can write simply this. Let's leave that.
Yes.
Right?
Yeah.
Okay, I'll come in a
Madam,
minute.
one thing.
I'll just
One-
come in a minute. Okay.
1 minute, madam. Can you write the same thing Q pi as in terms of V pi? That also.
Q pi in terms of V pi. Can we write? What do you think? What others think about that?
Yeah, we should be able to write, right? Q pi is immediate reward plus the value, the expected value from that next state, V of S dash. So the same above equation, the first term remains the same, the second term remains gamma into V of S dash. Yeah, that whole thing becomes V of S dash. Correct? I don't know. Yeah.
Wait a second. Is it the same? Is it correct by writing the second term? No.
No, no, no.
No,
No.
we have to make expectation thing. No. Correct? No.
No, this is Q pi S comma is for one action.
Yes.
Action. We take action and then we follow policy pi. This is we take action then we follow policy y.
Yes.
Yeah, yeah.
No, but
Now, give me a 1 minute break. I'll come. Just
Okay.
in a minute.
Okay.
Yes, let's proceed.
Please confirm. I wanted to write q pi of s comma a is equal to just can you write and then we think about it. Q pi of s comma a is equal to expectation of r given s comma a.
Wait a second.
Q pi of s comma a is equal to expectation of r given s comma a. R given s comma a, small r, yeah, whatever. Given s comma a, yeah. Then plus, okay, you close the bracket, plus sigma sigma over s dash, sigma over s dash, p of s dash given s comma a multiplied by v pi of s dash. Just
we can write.
Let us think, is it correct?
Wait a second. Expected reward given s comma a. That is what I was thinking. Probability of SA given S bar. Okay. If S and A are given to me, we can write this.
Right. So I want.
Is it correct for others? What do you think?
Because this is an important concept. So actually, these two are the beautiful equations.
Correct.
Once we master it, we understand the whole lessons.
What others think? Is it correct? S and A are given to me as Q pi, and then R, then what is the probability? If S and A are given to me, that I'll go to S bar and then future one.
Yes.
It's correct?
Yeah. Yes.
Correct. Okay. Now V pi, Q pi is cleared. Bellman equations for both of them. Should we proceed forward? We have less time. Should we proceed?
Yes. Yes.
Okay. Now, coming about what was taught in this, like before value iteration only, that the Banach space, okay, that how the value function basically converges and everything. Before that, I'll just cover some things which will be useful for you. Like, just first I'll write the things and then we'll discuss each of them. So these are the concepts which I used in order to prove. Why they are used, where they are used, I'll just tell you. First of all, what is Cauchy sequence? I'll come to the concepts. Don't worry, I'll join the dots. Can I say Cauchy sequence? When sequence in which all the elements are coming closer and closer to each other, that is the Cauchy sequence.
Yes. Yes.
What is complete normed vector space or Banach space? It is also called as Banach space. Can I say that if every Cauchy sequence is convergent, then the vector space is called as complete. On the same space, Cauchy sequence converges to the limit in the same space, then it is called as complete normed vector space. It converges to the same space. Basically, Cauchy sequence in this space converges to a limit that is also within that space only. That is basically called as Banach space or complete normed vector space. Coming to contraction mapping, what do you think? What is contraction mapping? Oh, sorry. If I have u, I have v, I have the function of u and v. So basically, TU and TV will be closer to each other. The distance between TU and TV will be less than the distance between U and V. This is basically the contraction property or the contraction mapping. Then what is the triangle inequality? These are the concepts which I'm saying. What is this? This is a norm. We are basically taking supremum norm here, which measures the size or length of the function. Max norm basically. We are taking. Are these four concepts okay?
Yes, yes.
So basically we are applying these concepts in MDP to prove the existence, uniqueness, and basically the convergence of that, the value iteration thing. What we are doing is basically first we know what is norm. Then what we are doing with the norm, we are also proving that it is the value function which we are proving is that it is in the Banach space. And then we are defining the Bellman operator there. Bellman operator, we know what is the Bellman operator, and then we are proving that the contraction of that, and with that contraction we are coming to the fixed point theorem, and that is how then we are coming that basically the algorithm converges. This is the whole procedure, the convergence proof. That whole takes these concepts, though we don't have time for the proof that we have covered earlier. Is it fine?
Yes, madam, but you can explain what is the use of these things, where we use this.
That is what it is basically when we are proving the value function that it is the convergence proof, that it is converging basically. In that place, that value iteration will converge to optimal value function to prove that these all concepts are used. First, we are proving. Wait a second. First, we are proving that it is a Cauchy sequence. Then we are proving that basically that Cauchy sequence is a Banach space, which means they are converging to a limit that is in the same space only. Then we are proving this contraction property that that Bellman operator is contractive, that T is a contraction basically, and then we are coming to the fixed point and proving the convergence. Basically.
Okay, I got it, madam. So basically, to prove that value iteration and those ultimately converges. Yes.
Is it fine?
Yes.
So this was the overview, just not going inside and giving the overview of this. That is why I came with these concepts. Now, okay, coming to value iteration and policy iteration. Can someone want to comment? What is value iteration?
Madam, just again a notation issue. When you say value, it implies both the V of S and the Q of S comma A, correct? Both.
Yes.
Okay.
Okay, can someone tell me what is value iteration? Okay, let's take a quick example, very quick example. I have this one. I take A1. I get the I'll take the action A1 and again go to S1, or if I'll take A2, I'll go to S2. I'll get the reward of 2. State S2. I'll go to S1 plus 1 reward. I am in S2. I'll go to S2 with the action 2 and I'll get minus 1 reward and gamma is 0.9. So first step is we'll initialize this V of S1, V of S2 as 0. Then we'll basically take the max of So whatever is this. So basically max of, I'll write here. The reward. What is the reward here? The reward is +1 plus gamma, that is 0.9. What is the okay probability? We are taking deterministic here only, and as they're initialized as 0, okay. And for the state 2, for this action 2, sorry, action 2, I got the reward basically 2 plus 0.90.
Madam, just one confusion here. When you take a max, are we considering optimum value?
Basically, we don't know whether it's optimal or not till now. We are here saying that maybe it's optimal or not. We are taking the max one here. At this point, this is giving me the best reward. This is giving me the best for me at this point. The maximum reward is given by, or the maximum whole return is given by the action A2, I can say. So it is the optimal one at this point. If I am in this S1, then A2 is the best one, optimal one.
Okay. Okay.
Am I correct by saying this? Anyone want to comment on this?
No, that's correct. Yeah, correct.
Okay, now let's proceed fast. So basically, V of S1 I can say, and V of S2, just I'll do one iteration I think because of the time. 3 plus 0.9. So basically, this is how I'll calculate by taking this, that this is 2 and this is 3. Again, I'll do the value iteration. Coming to the policy iteration.
Madam, just 1 minute. Go back. I have a doubt. The max bracket, no, the equation max, that the general equation V of S1, you have written max. That max bracket is for the entire thing, right? Okay.
Yes.
Yeah. Okay.
Okay, now policy iteration. What are the steps in the policy iteration basically? So I can say that policy evaluation as well as the policy improvement is there. That are the steps here. Basically, we are working on the policy here, more of the value function here. That is the main difference here. And now we'll start with, suppose any random policy. Suppose I say that A1 is the optimal one. This is my random policy which I start with.
We can take any policy, right? Here, there is no restriction. Any random policy you can take.
Yes.
Yeah.
So I have taken this. So A1 was 1 plus 0.9 V pi of S bar. This is how it works, I mean to say. And V pi of, S1 and V pi of S2 as I'm taking A1. So the reward is basically +3. It's going in second. So I can solve this equation. I can get the value, and then I'll basically do the policy improvement by taking which one will be the max one. This is how it works basically. First of all, any random policy, evaluate the policy, and then policy improvement is there. Okay, I'll just complete it. Suppose I get V pi of S1 is equal to 10 and V pi of S2 is equal to 12. Then what is the argmax of this? This is 1 plus 0.9 into 10, that is 10 here, and 2 plus 0.9 into 10, that is 12.8 here. So this is how basically I'll proceed. Both of the policies I'll basically improve. This is the policy evaluation as well as the improvement step. Now, proceeding forward, we have done these approaches. Now, what is value iteration? What is policy iteration? We got to know. Now, coming to the other concepts, RTDP, real-time dynamic programming, generalized policy iteration, both of them. What do you think why they came into picture? What was the limitation in value iteration, policy iteration? They both have their pros and cons. Sometimes policy iteration works better, sometimes value iteration works better. They came under one thing to solve the MDP. Why RTDP and generalized policy iteration came into picture?
Computations are heavy.
So what is RTDP? Can you brief out?
So whichever states which are followed, no, the states are on the trajectories. Evaluate, I mean, value function of policies along those trajectories only.
So can I say more effort should be given to compute the value function that we visit often, and
Yes.
less effort should be given to the function that to the states that we rarely visit. That is basically RTDP.
Yeah. Yes.
So now coming to this generalized policy iteration, what is that?
So something, I mean, asynchronous kind of, I mean, evaluation and improvement. You
Can I
can.
say I'm doing partial policy
Yeah.
evaluation, partial
Yes.
policy improvement in
Yes.
order to basically save that computational complexity, the time basically, or computational efforts basically.
Yes. Yes.
This basically this came to picture to save the computational power, storage, the time and all, which was very complex. So just focus on the states which are more valuable, lesser focus, or do the partial policy evaluation, partial policy improvement. That is why we came to picture. Now coming to Monte Carlo. Why Monte Carlo came to picture? The same reason, can I say?
Model
No, madam.
not available. Yeah.
Yes, model not available.
Can I say that it
model
is
free
model?
computation? Yeah. Model free computation.
Yes. So they don't require any transition probabilities and all, or rewards and all, can I say? They learn from their experiences. They are more easy to implement. They are more sampling based. They naturally incorporate exploration by sampling the episodes, I can say.
Yes,
They are
exploring from the environment or for simulation. Yes.
They are less computationally expensive as well as compared to MDP. Can I say?
No.
Why?
Monte Carlo it's not sample efficient, right? Monte Carlo, you have to take many samples to compute.
Okay, I agree to your point. Monte Carlo is also computationally intensive, but if we compare about MDP.
MDP, it is, see, the whole approach of Monte Carlo is when we don't have MDP. So we have to.
Yes. But MDP, can I say MDP is more computationally expensive because, or Monte Carlo is more computationally expensive? What are other people view about this?
No, MDP is exhaustive because we got the actual model. So Monte Carlo is Monte Carlo. It is a random, right? So
basically, we have the knowledge of the environment. We have all the knowledge. Here, we are not having the knowledge.
Yes.
Okay, let's. But usually, they both are computationally expensive in the other terms, I can say, because here also we have to do this due to the requirement of multiple samples and episodes. If I want to actually reach the optimal thing, then due to large number of samples and episodes, then this Monte Carlo can also be computationally intensive, basically. Now, what is first visit Monte Carlo and every visit Monte Carlo? Yes, come on.
See, in a first visit, in a particular episode, we are taking from a particular state. In order to compute the value function, the first occurrence of that particular state only we consider. Okay.
Yes, yes.
And subsequent we don't. Okay.
Yes.
So that means in every episode, we take only one value, the first occurrence of that value of that state only we consider.
If that state is repeated and we are taking that state also again, computing that, that is called as every visit.
Yes, yes, yes.
Basically, the first visit and every visit. Now coming to on policy and off policy. Can someone tell me what is on policy Monte Carlo? What is off policy Monte Carlo?
Yeah, in off policy Monte Carlo, we take any random policy for acting in the in the trials in a random. So we take any policy, arbitrary policy, we call as correct me, madam. We call as a behavior policy, correct? Anything to behave in the real world, which is maybe different from the policy we arrive at when we optimize it. So, for example, in a half policy method, so in order to start generating episodes, we do need a policy. So what policy we take? We take any random policy to start with. Any behavior policy, could be greedy policy, could be uniform random policy, could be anything. And then using that policy, we get samples, episodes, and then we try to optimize it. When you optimize it, that is the policy we are going to optimize. What we arrive at the end is the optimal policy. In on policy, we start with a policy which we wanted to optimize. So there is nothing like a behavior. In on policy, there is only one policy that we start with that policy gets optimized at the end.
Yes, yes. So basically samples are generated with respect to the policy we want to try to evaluate. But in off policy, samples generated by different policy, and we want to try, we want to update the other policy, that the different policy, as you said, that yes, it can be sometimes the random policy, it is indeed the random policy as well. And it is called as behavioral policy, and the policy which we are updating, that is called as the target policy. Am I correct?
Correct.
So what are rollouts?
Rollout means generating the trajectory starting from a state, following whatever policy, the behavior or basically rolling out from starting from a state towards the goal.
So basically, I can say, whatever policy you execute by rollout, we are having the different trajectories and then getting the average of them, all the rewards which we get. So here we can say that we can get the broader range of the expected return. If I have this trajectory, I have number of trajectories, I can have broader range of the, and how many trajectories should I have? Like, how much time I should run this trajectory? What do you think?
Yeah, as many as possible to get accurate. So
law of large numbers, okay. What others think? Yes. Yes, come on.
Ideally, the trajectory which visits all the states till we visit all the states.
What others think? Yes.
It's something called as variability. Income
Yes.
has to be considered.
It depends on the randomness or variability.
Yeah.
Say, if it is deterministic, if pi is deterministic, do we like? Is it like we have to run it as many times as possible? No.
No, not required. Why is deterministic is simple? There's only one trajectory, right?
So can I, yes, you are correct. So it depends on variability or randomness, how much randomness is there, or I can say how much computation time, how much time you have, how much computation you have, how much randomness you have. In these of the factors also it depends. Obviously, as you said, more of the samples if we'll do as law of large numbers suggests, more accurate we'll get. But if sometimes we do have this computational or time constraint, or I can say if it is deterministic, or I know that variability is very less, then why to run it for so long? So it depends sometimes on these factors as well. Now coming to Monte Carlo tree search. Now what we have done till now, MDP, MAP, Monte Carlo, and why MTCS, Monte Carlo tree search is required. Okay, before coming, okay, first of all, as you told me that you are confused between learning and planning. Is it clear to you what is the difference between learning and planning?
I try to explain as I understand, madam. So, in planning, what we do is we evaluate the policy much ahead before playing in the real world. That means, given an MDP, or even if MDP is not given, estimating the MDP and planning out means arriving at a value function for all the states. Basically, arriving at the value function V of S, all the states, so that we know each state is how much it is worth much before playing out. And,
Can I so planning is having some kind of specifications? I have the model. Basically, MDP is planning. Can I say that?
Yes,
Yes,
exactly. Estimating an MDP computing the value function is actually the planning activity. And learning activity. Oh,
okay.
sorry.
Yes. Come on.
Yeah, learning is actually is playing out in the real world, and and taking the rewards and then updating the policy as we play out in the real world. That is called learning.
Can I say without knowing any of the parameters ahead? It's the agent collects samples, observe the rewards, update its knowledge based on the received feedback. This Q learning and all, they come under this learning thing.
Q learning, yes. Q learning, provided MDP is not known. Basically, learning means there is no MDP at all.
There is no transition probabilities and all known, model known to us.
Yes.
Okay. Now coming to MCTS, Monte Carlo tree search. Can I say that it is basically combining the benefits of both the Monte Carlo with the tree search technique? Basically, tree structure, it gives us the structured representation, what decision we have to make, where each node I'll represent as state, edge as the action, whereas we can have the Monte Carlo simulation as well. Basically, that is basically we are combining both the benefits of Monte Carlo with research techniques, and also applying the basically the Monte Carlo simulations. If I give the, wait a second. It basically
you can explain it better, madam. So this is you can explain it once again.
I think I haven't taught this topic.
Yeah, this is important. In fact, this is the one used in AlphaGo, I think, right?
In the game of Go, basically this is used here, correct. Before going to that, what is in the Go game, like what algorithm does, it expands the tree by adding the, okay, first of all, these are the 4 steps which are involved. We start at the root node, and now algorithm selects the child node based on the selection process. Basically, it will select which is the child node, that is the selection process, sorry, which one will be the child node. Now, if the leaf node is not the terminal node, the algorithm will expand the tree by adding one more child node, representing what are the possible actions, basically. Then simulation is performed basically from the newly added child node until the terminal node. And then again, the result of simulation is basically back propagated up to the search tree, updating the value estimate and the number of counts, basically everything is done there. This is the whole algorithm, searching, then saying that it is a terminal state or not. If it is not the terminal state, then basically selecting the action and basically adding the one more child node, then doing the simulation basically, and then back propagating to update the value function. This is this. And in the Go game also, in each iteration basically, the algorithm is expanding the tree by adding new node. It represents the board position. Then games are simulated. For each node, numerous games are done, simulated with some random moves and all. And then the outcome, basically, whatever the outcome of the games, they are used to update the values of the nodes, basically. And move is most promising child of the root. That is basically how move is made. And based on the simulation, it is chosen as the next action, basically. This is just the overview, which I tried to explain in just few words. Though I haven't explained the topic, I don't know how you have gone through. I told the other TA to explain the next day when you told me that this was not explained in the class, the previous lecture. So is it covered in the class? Why everyone is silent?
It is covered, madam, but no, don't know. Quickly gone through something like that. I heard this word.
Okay, what about others?
Yes, he has discussed it.
Okay, do you got this? Can you give the summary of this? Basically, I'm selecting a root node at the tree, which is the current game state. And then I'm traversing the tree by choosing the child node, basically. Selection, it is based on some okay. And then what I'm doing is, if the selected leaf node, it is non-terminal state, then it creates one or more child nodes for the possible actions. Then Monte Carlo simulation is done. And then I'm back propagating, basically, updating the value, visit of the counts and all. And then after the search is completed, the action is basically made, which is basically leading to the higher value. This is the overview of this MCPS. Okay,
Madam,
if you
here
want,
in this algorithm, function approximation is involved, right? You are using back propagation.
No function approximation. Okay, the selecting action is as per policy or any action?
selecting action, it can be based on the specific policy, like upper confidence bound, UCB and all.
Okay.
Basically, I am in the start node. I select the action based on some specific policy like QCT, and then the tree is expanded, and then the simulation is made, and then back propagated and updated the value functions. I get a summary. I thought that the detailed thing is covered. Okay, if you still have doubt, then I can say that TA to explain in detail. Is it fine?
Okay.
So I tried it. Okay.
No, madam. Anyway, we have to read once again to understand. Maybe you can skip this. You can go to some other topics. Yes.
Okay. Now coming to dynamic programming, Monte Carlo, TD methods. We earlier also saw what is the difference between them. That full backups are there in DP, sample backups are there in Monte Carlo, sample backups are there in TD learning. But bootstrapping is there in dynamic programming as well as DP. Dynamic programming as well as TD learning, whereas bootstrapping is not there in Monte Carlo. So basically, TD learning is combining the like ideas of both DP as well as Monte Carlo. Clear? If you want, I'll explain in detail.
It's okay. That's clear.
That's clear. Okay. Now, what are the topics left? I think I'll tell him from where I have ended the revision. He should start the topics from there. Okay, I'll go ahead though. Now coming to SARS and Q learning. It's like many things are covered, still many things are remaining. It's looking like to me. Okay, now one question is, we studied about this. Is SARSA, SARSA and Q learning, are they Monte Carlo methods or are they not Monte Carlo methods? What are your views? Till now, everything what we have revised, is it clear? Like, how was this revision going on? Is it smooth?
Okay,
Is it-
fine, madam. Fine.
Okay. What is
SARS? Yes, SARS.
They're for TD learning, right?
they are for TD learning. And they came into existence, I can say, to give a middle ground, I can say, as we discussed, to DP as well as Monte Carlo methods. They are basically having the both of the concepts of, I can say, both the concepts of Monte Carlo as well as DP here. And
Yes.
that is what. And now going to SARSA, basically, not explain that. Okay, which one is on policy, which one is off policy?
SARSA is on policy.
So SARSA is basically on policy, and I can say this Q learning is off policy. So basically, major difference I can say between SARSA and Q learning is that it is chosen according to the current policy, the SARSA, whereas Q learning is basically not like learned according to the current policy.
Both are model free, correct? Model free.
Both model free.
Right.
So should I give you how we solve it, or is it clear to you how the update?
Q learning, if I've gone through the example, it appears to me like a TD, one-step learning. Am I correct?
Q learning and SARSA, they are TD learning methods. They are TD.
Yeah, in Q learning, actually we learn the Q function, right? Q value for every state. And from that state, we arrive at the policy. Whereas in SARSA, also SARSA also we learn Q value, right? Q value. I don't know. Maybe you can explain a little SARSA about it. Yeah, Q learning, I understood. SARSA is still great.
We are learning value function basically. I'll tell you. Okay, let's go in the of SARSA. What is the full form? State action reward, state action on policy. Basically, I can say that Q of SA is Q of SA this is the update rule which is used basically in the SARSA. Then if I talk about example, I can't, okay. So should you do you want me to give example, or I haven't prepared for the example as well. So basically I'm having state action reward and
Madam, can you write a similar equation for Q learning? Because both seems to be same for me.
Okay. Okay. Wait a second. There also the max is there. That is what I'm thinking. Can someone explain the difference? Yes, come on. Yes, yes.
So here in SARSA, we select, we select action in the next state. But in case of Q learning, we select that action which maximizes Q value in the next state.
Basically, Q learning is estimate the value of Q values based on immediate reward. Can I say that? And the highest.
Higher maximum, yeah.
Huh.
The Q value which maximizes in the next state.
Yes.
So we do not require to select next state in Q learning. But in case
Yes.
of SARSA, we need to select next state.
Yes. Is it clear?
That's why we can have policy in case of Q learning.
No, but we see Q of S dash comma A dash in both the equations, correct?
Can you see that max thing?
This max is for only Q S dash A, not the square
Wait a
bracket.
second. Yes, yes, you are correct. It is for only this.
Yes.
Oh, yes.
So basically, Q value is updated based on current state action and the maximum Q value for the next state, as he told. In SARSA, Q value is updated based on the current state and the next state action pair as well. Can I say?
Or we can say Q learning is just one immediate state, and SARSA is next state and action both.
Next state, yes, current state and the next state action both. Can we say that? Is he correct by saying that?
Current state and next state and action. That's why SA, SARSA.
Yes.
Whereas
Is
pure Q learning is a SARS, SARS. Can I say that? No. Yeah.
You can't.
No.
We can in Q learning we can select any state and action, and we can update that QSA. But in case of SARSA, we should have up some policy and then select A and then next state as per policy.
Oh yeah. We have to take policy, so we have to put pi there.
Yes. So let's proceed forward. So as you know that in the Q learning, we'll initialize the Q table first of all with all zeros. Then exploration is there, then the interaction, observe the immediate reward, then the Q value will update it and we'll update the states as well. So it happens in the episodes there. Now coming to, okay, I think we covered the important sampling. Okay. The legibility traces or okay. So what are the things which are covered, are they clear to you today in today's lecture? So what is left?
We have to revise. I mean, no doubt.
Okay. But some way I thought that let's see what's the limitation in the previous one to try to basically connect the dots and all.
Yes.
So I think from eligibility traces it's left. You want him to start from the starting or from the eligibility traces he can give the overview? What do you think?
Eligibility traces. First 6 weeks are covered now. Only
First 6 are covered. I'll tell him to go with the next 6 then. And still, if you have any doubt, you can mail me anytime. I'll reply.
Madam, one fundamental question. See, the goal of reinforcement learning is actually to discover the optimal deterministic policy, right? When you say optimal policy, it will invariably be a deterministic policy, correct? Can I make that statement? Given an MDP, given states and actions, set of states and actions given an MDP, or okay, MDP is given or not, that's a different matter. But whatever it is, model or model free, ultimate goal of reinforcement learning is to discover an optimal policy, which is nothing but a deterministic policy. All optimal policies are deterministic policies. Can I make that statement?
Optimal policy, yes. Deterministic policy can, okay.
Need not be always deterministic.
That is what I'm thinking. They can be stochastic also. Yes.
Yeah, I'm not able to
It may happen that following two different actions, we might get similar rewards.
Yes. I think we have also done that. Policy can be multiple, but the value function will be unique.
Yes, value function is unique.
Oh, value function is unique.
There can be multiple optimal policies.
Yes.
Multiple optimal policies. That means stochastic.
Not stochastic. There a policy itself might be different, and stochastic policy is different, and multiple optimal policies are different.
Okay.
The policy itself is stochastic. Then that is the case.
No. What I'm making is, let us say the ultimate goal is we have to discover optimal policy. Am I correct? That
yes. Correct.
So now that optimal policy, what you are saying is we can have multiple optimal policies.
Correct.
But all these multiple optimal policies are deterministic policies only, no?
Are they? I mean, that is the question that you asked first, right? So thing is, I mean, it can be a stochastic also. No? Optimal policy can be stochastic also, right?
If we are talking about non-stationary environment,
correct,
where dynamics change over time, then the stochastic policy is also changing now over time. It is adapting to that. If we are saying that environment is changing over time, as we also saw in the epsilon greedy as well, you told me, after some time maybe that A is not performing better because maybe A is not performing better. Maybe that dynamics change over time because of the
so can you give example of deterministic and stochastic policy, for example?
Okay. So, I can say that deterministic means that environment is deterministic. The policy will not change the rewards itself.
So probability of some action is 1, right? Is deterministic policy.
Yes.
And let's say think of some state. So in that state, probability of some action is 1, other actions probabilities are 0. That is deterministic policy, right?
Suppose it's there, and due to some case, this goes to 0.7 and this goes to 0.3 because there is stochasticity in the environment, I can say.
So thing is, we need to update policy, we need to explore, no doubt. In that case, policy would change. But let's say if the environment is stationary, not changing,
okay,
then can we have stochastic policy?
Okay. If the environment is not changing,
then can we have stochastic policy? That is, in a state, can we have non-zero probabilities for multiple actions? Still getting same highest value function, still getting optimum rewards. Follow the optimal path like that. Is that the question, Gopal sir?
Yeah, no. When you are saying that in a particular state, all actions have a probability 1, that means you are talking about...
No, one action will have probability 1, other will be 0, not all.
Then that is deterministic policy.
That is deterministic. Yes,
there is only one route to success.
Correct.
Yes.
So that is what I thought. That is the goal.
But in case we might have optimal policy in which in a given state we can have multiple non-zero probabilities to multiple actions. Can that happen? Can that happen?
That is called stochastic policy. No?
That is a stochastic policy.
Yes.
But if it is stochastic policy, see, actually it boils down to my common sense. Intuitively, if the game is stochastic, why is the question of optimum? No, our goal is to discover a root. If the root itself is a stochastic, then what do we mean by discovery? So I'm just trying to reconcile in my mind, the common sense logic. When somebody gives a maze, okay, so yeah, you try to discover the root. So you assume that actually in a maze there could be several routes. That's okay. There's several optimal policies. But whatever is the policy route I discover, that is clearly deterministic policy route.
Actually, the policy have to adapt with that changing route. That is the main thing.
Okay. But somewhere I read that an optimal policy has to be deterministic, and I don't know the context. In which context that statement was made?
I think it can be stochastic as well.
It depends upon application.
It depends on.
So depends is always a yeah.
It depends.
Yeah.
No, if
Always a joke in the class.
Yeah, if everything it depends means, then the whole problem is solved.
Simple answer, it depends, yes. So, how was the whole session? So, this was the last lecture.
It was good. Thank you. Thank you for, still taking a lot of efforts and getting us to know something at least. Decode what your professor talks over there. So, and solving examples, going through once again all the derivations. It was great to hear. And then once again, regrouping is very important. Yeah.
Yes.
So these sessions are for that purpose. Yeah. Thank you.
Yes.
Thank you for that. Thank you. Well done. Thank you.
Thank you so much, everyone. All the best for your future. Thank you.
Thank you, madam.
Thanks.
Yeah, thank you for your efforts. Thanks. Yeah.
Thank you.